All right, so welcome back, everyone. And today we will be talking about probability. And now that you have known a little bit more about R, either or not you have R experience before, using the previous recording, and you have just got familiarized a little bit about the practical considerations of using R. You know the data type, matrix, vector, data frame, data list, and so forth. And now today we switch gear a little bit. We will have a rather theoretical lecture about the topic probability. And most particularly, we will be talking about probability, the differentiations in terms of how we describe events. And I will explain that to you. And if the time allows, I will also show a little bit more about how to plot probability distributions in R. Let's see if we have the time or not. Okay, anyway, probability is something that I believe everyone knows and everyone is aware of, and everyone, I would say, is rather confident about describing, because we use the term probability nearly every day, right? And for instance, this week is pretty rainy. I guess everyone, when you are going out for grocery shopping or when you are going out for a running, I guess you do have to check the raining probability to decide if you really want to go, or if you do have to go, do you have to bring an umbrella with you? So something like that. And as simple as that, probability, do we still have anything to talk about? Well, the answer actually is yes. So even though we use it, we talk about it every day, and then there are some properties that we have to keep in mind when talking about probability. So the most important one is, we know that probability is like a number that is assigned to describe possibilities, and the value or the range of probability is always in between 0 and 1. So if a probability of 0 basically means that this thing or the event will never happen, and if the probability is 1, then that means this event will definitely happen. And then if the probability is anything in between, okay, 70% tomorrow afternoon, it will be raining, or 30%. So then this is like a uncertainty measurement. And another important property is that if we know that one event that has multiple possible outcomes, and all the probabilities that are corresponding to each outcome, they sum up to 1. What that means. So if we have a coin, we only have 2 sides. So one is the head, the other one is the tail. So assuming that we have a fair coin, and if we flip, and then we will get 50% of the time the head will be facing up, and then 50% of the time the tail will be facing up. So in summary, in short, that means we have a event. So we throw a coin, and we have 2 possible outcomes, the head or the tail, and each of them is 0.5, 50%, and 0.5 plus 0.5, it equals to 1, right? And assuming that if we have an unfair coin, and then the probability of facing up, that the head facing up is 0.4. And you don't have to think too much. You will immediately find out that the probability of the tail facing up is 0.6. So 1 minus 0.4 is 0.6. And now you know this kind of meaning of the second property. And another example, really simple and everyday example, is we have a dice. The dice has 6 sides, and the probability of getting 1 point, 2 points, 3 points, or dots is 1 over 6. And if you sum them up, it's 1, right? So as simple as that. Great. So probability is as simple as that. And probabilities are used to express uncertainty. And then what was next? What do you want to know? if we want to know a little bit more about probability, or what are the elements that we are not so familiar with regarding probability. So it turns out that when we are using probability to describe events, we have to make one differentiation in terms of the type of the event, or more precisely, the type of the outcomes of that event. So if we have a coin example, we could only have two possible outcomes, head, tail, nothing else. And if we have a dice example, we only have 6 possibilities, 1, 2, 3, to 6, until 6. And what are they? So they are discrete possible outcomes. They can be only that many possible outcomes. If I give you a dice, you can never get 1.5 because this is not part of it, right? This is only the cube, and then 1.5 is not possible. So this is discrete events. And conversely, the probability of winning, you can say, well, it can be 70, 71, 71.1, 71.111, right? This is a continuous scale. So the probability of winning, this is an event. The possible outcome in terms of using probability to describe it is infinity, right? This is continuous. So when we are talking about continuous events, versus when we are talking about discrete events, we use different terminologies, slightly different terminologies, and also different visualization techniques to describe probability. So the first one, when we are talking about discrete events, so the terminology or the term or the phrase or the expression, whatever, to describe probability is called mass, or simply probability mass, or probability mass function. So one example here, this is a slightly different example. So let's say I give you one example, one exam, and then the exam only has 8 questions, right? And imagine and ask a few of people, 100 people in the classroom to finish the exam. And what are the possible outcomes? So some people, they might answer all of the 8 questions correctly. And some people maybe 7, some 6, some 5, 4, 3, or in some cases, nobody, or in some case, some people will have none of the 8 questions answered correctly. Okay, so there are 8 plus 1, 9 possible outcomes. In this case, answering the number of correct responses, so either 0, 1, 2, until 8. Discrete events outcomes. And what we can do now is, suppose we ask 100 people to finish the exam, as I said, you could do a histogram to count how many people answered 8 questions, every question correctly, how many people answered 7 questions correctly, and 6 and 4, 6, 5, 4, 3, 2, 1, and also 0. And then we get this kind of histogram, a plot. And then this histogram, this kind of histogram to describe these discrete events, this is the probability mass function, okay? But what we can do, as we could imagine, to give you one more example. So let's say we have a coin, right? We have a coin here, and there are 2 possible outcomes. So one is the head, one is the tail, right? And imagine what could be the possible probability mass function of it. Well, you don't need assumption. Well, I can tell you. Well, you don't know the assumption yet. I can tell you the assumption. So let's say I tell you, well, the probability of getting a head equals 0.4. It's a little bit unfair coin, whatever. Good. So now you could imagine, just maybe if you have a paper and pen aside of you, you can just draw it. I give you 20 seconds. So if you have a histogram and you have a x system, x-axis and the y-axis, and the y-axis is definitely a probability, and the x-axis, what is that? Well, you can say, because there are only two types of outcomes. One is the head, then the other one is the tail, right? The other one, yeah. Now how would you draw it? I guess 20 seconds has passed. So if you flip this coin 100 times, then you count the frequency of head, for example, probably 41, because there are some randomness here, 49, 59, yeah. And also because we are not interested in the frequency alone, we are also interested in the like proportion or the probability. Okay, we divide everything by 100. Good. And then we make a plot. Yeah. So here, 0.4, around 0.4. Here, around 0.6. Right. So this one, even though it's quite simple and straightforward, I guess, but this is already a probability mass function. Okay. Now what we can do, we can also think about the dice example is also quite straightforward. We have a dice, one dimension of it. Here this is 1.1. And we have a plot. We have 1, 2, 2, 3, 4, 5, 6. Yeah. And suppose this is a fair dice. Every side will have a 1/6 probability facing up if you toss it. So what we can have, we have a histogram like this. Not drawing very perfectly, but this line, supposedly it should be the same, right? So this is another case of a probability mass function. So maybe probability mass, the term per se is new to you, but the idea of getting this function, and this function is simple, it's straightforward. Everyone can do it. Okay, cool. So now we go to the next one that is interesting. So the next one is when we are talking about continuous events, we use another terminology to describe it, which is called probability density or density function. So I believe everyone knows normal distribution. Then this curve, like the bell-shaped curve, everyone knows about it. This is already the probability density function of a normal distribution. And when talking about continuous events, there are actually two types of density functions. So one is the probability density function. So here it's called PDF, not the PDF we have, but probability density function, PDF in statistics. And then there is another one, which is called the cumulative distribution function, or the CDF. I think everyone is familiar with PDF, but what is CDF? Or maybe how to understand or how to explain the cumulative part. So here is the idea. So recall that probability, the two properties that I told you at the very beginning. One is it is between 0 and 1. Okay, everyone is happy with that. The other one is if we know all of the possible outcomes, if we sum up all of the probabilities, they have to sum up to 1, right? So, oops. So here in this case, if we sum up the length, all of the lengths together, and all of the value together corresponding on the y-axis, you will get 1. This is for sure. And also the head tail example, I have only 2 bars. One is a little bit shorter, the other one is taller. You sum them up, then you get 1. And the dice example, all of the 6 instances, they have 1/6 value. If you sum them up, they are 1. Okay, good. Easy to understand. But what is the 1 here? If you have a continuous event, tell me, so think about it, or you tell me, where is the 1 part? What is 1? Where is 1? How can I get 1 from this figure, from this plot? And it turns out that because this is a continuous curve, right? This goes to infinity negative, this to infinity positive. So if you take the area, entire area under the curve, this is 1. So if we have a continuous event, if we have a probability density function or density function to describe the shape of the probability distribution, the area under the curve is 1. And always remember that, this is very important. So then, in this case, well, some people are interested in visualizing the 1 because they want to get 1, and then they want to say, hey, if I have 1, if I see 1, I'm happy, otherwise I'm confused. So then how to get 1? Imagine we could come up with kind of a visualization approach. We plot it, and then the x-axis, it will remain the same as the one above. Here is 50, the other one is 90. Okay, good. And imagine we would like to have some kind of visualization or calculation to get the exact value 0 and 1. How do we do? So we want to construct a plot such that the x-axis is identical to the original PDF probability density function. And at the same time, we would like the y-axis to be really the 0 and 1, rather than here. Here, I didn't even show you. I will tell you later. This doesn't make sense to show first, and I will explain to you later why I don't even show it. Okay, good. We want this. So how do we do it? The idea is, again, no. Yeah. Yeah, okay, cool. So the idea here is, again, to use the area under the curve. So I told you that the entire area under the curve is 1. But what about I use only part of it? So what I can do is I draw a line here. I draw a line, and then I calculate the area under the curve up to this line. So then I go down to this line, and then say, I know that the entire area under the curve is 1. So this part, it must be something below or in between 0 and 1. And in this particular case, it is slightly below 0.5. Let's say I have a calculator, a computer could help me actually to calculate the exact area under the curve. So I calculate it, and then I plot it on the y-axis on the plot down below, okay? So here's 0.5, and then the plot there is a little bit smaller than that. So let's say it's here, okay? Let me use a different color. Yes, here. And then let's say here, this line, this is also a moving line. It moves from the negative infinity to positive infinity. So we have a line here, we could do the calculation, we plot it here. And then we have a line here, we do the calculation. In this case, it will cover a larger area in the curve, right? It's somewhere here. And when it approaches infinity, and then this will be very close to 1. Right, does that make sense? So I have a moving line. It moves from the negative infinity to the positive infinity. And each line, in each time when the line is there, it calculates the area under the curve at the left-hand side of the PDF. And then the returning value of this subsection of the area under the curve will be plotted on the plot down below. And then what you could imagine here is like in the end, it will be a curve like this. It will be a curve like this. So that's why also the reason why it's called cumulative distribution function. So because if we have a distribution, we have a line here, we do the calculation. If we have another line, if we have another line, then the area under the curve is here. So here, this part is counted twice. Is on purpose. So this is accumulating. The area under the curve is accumulating as the line moving from negative infinity to positive infinity, right? So we get a cumulative, like increasing summed area of the curve. Great. So now, without all of the ugly drawings I have, I show you how it actually looks like. It is like this. So this is the same one that I showed you, and this kind of XS shaped curve, or in the literature, people call it sigmoid. Sigmoid, that means S-shaped curve, is the cumulative distribution function of the normal distribution. All right. Short summary, we have continuous events. We have two types of probability density functions. One is the PDF, the other one is the CDF. CDF and PDF, they are not unrelated. In fact, they are closely related, and you could derive from one to another. If I show you the PDF, you can actually tell me the CDF. If I show you the CDF, you can actually get it back to the PDF, right? So there are some analytical approaches. We will not talk about here, but it is possible. And the next one I want to tell is, no, so there's one more example. It's the same idea. So here the line is around here, and when the line is moving from this 65 to 70, then the area and the curve is getting larger, and we are moving from this dot to this dot. Okay, perfect. And now there is a question from the chat. So wait. Yes, Annika is asking, do we use that for the logistic regression or not? No. No. The reason is, it actually explains a lot. Yeah, let me try to. Okay. We have a shape of this. This is the CDF of the normal distribution, right? Good. And if you are familiar with logistic regression, and you are also familiar with the sigmoid curve that is used there, and that is called the logit. They look pretty much the same, but the mathematical equation is entirely the difference. It is entirely the difference. So in the literature, let's say this is the normal one, the normal CDF. The normal CDF in the literature is called probit. In fact, it is the reversed probit. This is a little bit maybe too much for the course. If you don't know, don't worry. And I will just quickly go through that. This is called the inverse probit. And then this one, let's say this is used for the logistic regression. Well, then this is called logit. And also with a minus, that's the inverse one. The shape is pretty much the same. And the difference is, I think if I get it correctly, so the logit is a little bit steeper, a little bit, I think. I might be wrong. I'm not sure. Yeah. So it's really a little bit difference. So in terms of application, so if you want to use it, you can also actually use this one for logistic regression, but then you don't call it logistic regression, you call it probit regression. The result, the parameter estimation, I guess it would be the same, but theoretically they are different. They're completely two different things, even though they look super similar. And there is a Wikipedia entry, I think, they actually explain the difference between the logit and probit. Great. And then there's another question, and I can get back to the slides. So the question is asking, is the PDF the derivative of the CDF? It's related, but not actually the case, I think. So what I can say is, so if you know derivative, right? If you learn from school, so here if you draw a line, then for this line, the slope of this line is the derivative of that point, okay? Oh, wait. Yeah, I think you're right. So I think I should draw it here. So if I am taking the derivative of the CDF, then this is very steep, and then here is not steep, and here is also not steep, right? So what we want to do now is we could, So what we want to do now is we have another plot. The x-axis is the same, 50, 90. Okay, I just don't want to write a 0. And we now kind of write the derivative, so something like this. And then here you can see, well, this slope is small, right? And then when the curve goes from here to here up to maybe the center point, so the derivative goes high. And after the center point, then derivative goes smaller and smaller. Yeah. So what is that? That is it, right? Yeah, this. I think so. Yeah. Yeah. So you're right. Good. So now you understand it better. If I give you CDF, you can just draw the CDF for me. If I give you the CDF, you can also get it back to the PDF. There's a one-to-one mapping. Yes. All right. Another short summary. So far, we just didn't talk about too many things. We just only talked about two types of probabilities. One is the probability describing discrete events. So we use probability mass function, histogram, right? Everything sum up to 1. So when we have continuous events, we use probability density function. We have a curve, continuous, and the area under the curve, under the entire curve is sum up to 1. And the PDF is one way to describe the probability density function. There's another way, which is CDF, which is now that you see the cumulative density function. And then there is a one-to-one mapping between CDF and PDF. You get one, you get the other, and the other way around also works. Great. And some more examples so that you really understand it. And this is let's to say, well, we have a set of numbers. We have 1, 2, 3 until 100. And let's say you don't really know it. There's a bag, there are 100 balls, and on each ball, there's a number written on the surface of it, 1, 2, 3, 4. And let's say you close your eyes, you draw the ball, and then you get it. Well, the probability to get each number among 100 is just 1 over 100, right? So if you do a plot here, the x-axis is all the possible discrete outcomes from 1 to 100, and the y-axis, the probability, so frequency divided by the overall 100. This is the same as the dice example, just more possible outcomes. And now here, this one is to say, I guess you are familiar with this sign. So here, this one means summing up. And you sum up all the possible x, and then it is summing up to 1. So it means if you sum up 1 over 100 for 100 times, you get 1, right? Good. So since we are now talking about this capital sign, so maybe I will explain that a little bit, because I'm not sure if you know about that. So let's say we have a variable called x, and we have an index called I. So here, this expression simply means I want to sum up from 1 to 2, from 3 until 100, okay? So this is the sum sign, summing all of the possible x from the first written in the bottom to 100 written on the top. Okay, sum. And then there's another one which is called pi. Well, we know this pi, right? 3.14. This is a smaller letter, like English or German letters. There are small letters, small cases, and German cases. And the one I wrote here, this is the bigger or the capital case. The capital case, if I have also a xi from 1 to 100, so this is a product sign. So instead of summing from 1 to 100, it now just multiplies everything. x1 multiply x2 multiply x3 until 100. Okay. Honestly, this is not so widely used in when we are describing things. It is widely used in statistics and physics a lot, but not so often in our field. But it's better that you know it, I guess. The sum sign here instead, it is pretty helpful. So it is to simplify your expression. If you want to write it this way, it looks not so difficult, but it can get complicated if you have a complicated model. And then using the sum sign, it really gets a lot simplified. All right. So here we are giving an example of discrete events. And now I have the example of a continuous event. So here, the continuous events, the example I'm giving you is the height distribution of here, the entire Austria, let's say. So we know people's height, this is a continuous variable, right? People can be 160, people can be 170, people can be 180, but people can be like 181, 182, 181.5, for example. So everything is possible. It is the entire continuous space. So the interesting part is actually here. So if I ask you, what is the probability of a person being 180? What is the probability of that? The answer is actually 0. Does that make sense to you? So you can think of this way. So let's say we have the entire population and then the height is the distribution and it is infinite and there is unlimited possible height. But let's say I know really one person very precisely using the most precise ruler in the world. And then to measure that person is 180. Okay, good, whatever that exists. So 180. But remember how to calculate probability. What is the proportion of observing this person over the entire population? This is infinity, right? And then what do you get? You get 0. So on a continuous space, probability density function, when we are having kind of this function, any value on the x-axis, if you are interested in the probability of this value, will always 0. If you are interested in probability of 0, this value also 0. It's just 0. It's always the case like here. You have exact value and divided by infinity, you get 0. Good. 0 doesn't make sense here, or it's not so informative. What can be informative is instead we can calculate the area under the curve again. So we can calculate the area under the curve if we draw one line, but we could also calculate the area under the curve if we have 2 lines, right? If we have 2 lines, then we can calculate the area under the curve like in the middle. So now in this particular case, I'm telling you here, if let's say instead, I'm now interested in the probability of people who are taller than 175 but shorter than 185. Okay, now they have a range. If now I believe that the entire like height distribution is normally distributed, I know the curve, so then I will just be able to get the area under the curve. So instead, I will just know the range rather than I'm interested in a point. Okay. So now another question that I didn't explain yet is if now let's say again we have like normal distribution, and I didn't show you the y-axis, but let's say I just want to see it. How can that be look? How does that look like? So 0 is fine, it's always here. But what is this? Is there an upper limit? Is it 1 or can it be anything else? The answer is there's no upper limit and it can be anything. It can be even above 1. So what that means? That means this is the relative density. This is the relative density. We know that here is higher than here. Here, this is the highest. This is fine. But the exact value of it is quite arbitrary. So we have this is a wider distribution, and we could also have a really stupidly narrow distribution, right? Like super narrow. And we know the assumption that the area under the curve is 1, and then the area under the curve is also 1. So if it is narrow and we want to maintain the entire area under the curve to be 1, do you agree that this actually should be very high and very tall? I'm not sure, but maybe 20 or something, even higher. So this number really doesn't make so much sense. It's arbitrary, it's relative, and doesn't really give you too much information. But it can be confusing sometimes. Great. Any questions up to here? All right. So if not, if we are, oh, sorry, there is a function, a question. For standard function, it should be max 1, right? Not sure, and I don't know that. I think no. I think it's also point is below 1, I think. But you can Google that. You can use Google Wikipedia and then you say about standard normal distribution, and you find, and then click picture to find the plot, and then you can see if the max is 1 or not. Okay, there's another more general question. So let's see. How are effect size in psychology or neuroscience distributed? Do they follow normal distribution, or does it depend on what one looks? Yes, I think so. Yeah. It depends. Depends on the experiments, I think. This is what I mean. Well, there are two things. So one is this really a strong one in the first place? So let's assume there is a truth, and we are using experiments to detect it. And this is related to the sensitivity of the experiments, or like the beta if you are calculating effect size, right? And then, or 1 minus beta. And then, so there are just basically two things. One is the ground truth. We know or we don't know. The other one is how sensitive that we are able to detect it. Maybe the sensitivity is around the truth, but I'm not sure if the so-called truth is normally distributed. I'm not quite sure. Yeah. This is largely related to experimental design. And another one, in the height example, do we really have infinite possibilities? There is an upper limit to height, and we can only measure a certain accuracy. Yeah, the assumption is you never know, right? There can always be a Guinness World Record highest, tallest person or shortest person. Yeah, you never know. It can be. Or maybe I use another example when you really agree that the numbers are infinite. So then that's easier to explain or to imagine. Other questions? All right, so if not, so here you can try it at home later afterwards. So if we are now focusing on the normal distribution only, and we know that we have the PDF, we have the CDF, and the related or around a normal distribution, there are 4 types of functions in R. So here in this case, norm, this letter is the letters, they are always the same. So they just basically mean normal distribution. Around or associated with normal distribution, there are always 4 letters or prefix letters around it. So what are they? The D here corresponds to the density function. So D norm means the probability density function of normal distribution. So here the P norm that is related or equivalent to getting the CDF, the cumulative density function. And then the Q norm is the quantile. Okay, this is the inverse of the CDF I ever explained. And then the R norm, it is the random number generation. And these four letters, the DPQN, is the same for all of the distributions. Let's assume that there is a distribution called gamma. It exists, I didn't make it up. There's a gamma distribution. You can say, well, D gamma, P gamma, Q gamma, R gamma. It applies to every distribution. You can have Bernoulli distribution. We will see later during the course. You could have D Bernoulli, P Bernoulli, Q Bernoulli, and R Bernoulli. These four letters applies to everything. So now we can take a look at how that works in R, and you can try it. I really encourage you to try it at home. So now I'm just generating 4 plots using each of the 4 functions. So the D norm, I think this might be the standard normal. So here you see this is 0.4. Whatever, regardless, so this is the density, the PDF function. And the P norm is the CDF. I showed you how that works. You know why this has the sigmoid S-shaped shape. And the Q norm is the quantile. And the R norm is random number generation, assuming if I randomly generate 1,000 samples from this distribution, and essentially, if I sample enough, it will also follow the distribution of this one, right? This is easy to understand. So what is a little bit tricky is the Q norm. So Q norm, as said, it is related to the P norm. It is inverse. And how does the inverse function works, if you know? So the inverse function works like this in statistics. So if you have a function in general, if you have y described of a variable of x, you could then also be possible to do the other way around, right? You could just flip the axis so that you have x, which is displayed by y. So this is the inverse function. And to visualize that, that is here. So we draw a line like 45. So this is 45 degrees, 45 degrees. This is the identity line. We draw a line here. Now x becomes y and y becomes x. So then we draw a new curve again, like we do a mirror with respect to this identity line, with respect to this 45 degrees line. So what we will be able to obtain is you just mirror it, right? You do a mirror, do a perfect mirror. Not so perfect, but imagine this is perfect. This new curve is this. This is the inverse one. So it is the inverse function. Okay. Good. And so why do I call it quantile function? Right. This why do I call it a quantile function? So this is related to the x and the y the meaning. So let's say if I have kind of a distribution on the x-axis, it goes from negative infinity to positive infinity. And now if I give you a number and you could get the cumulative property or cumulative probability up to this point, like related to here, right? This is how that works. So now let's say I have a sample. I want to know what is the, I have a sample from negative infinity to positive infinity that is normally distributed. Now I'm curious about what is the percentage 75 on this entire sequence. Now I enter 75 because I want to know the 75% quantile. So that's why it's called quantile function. And then I get this value So I say, well, this 0.7, for instance, is 75% quantile on this entire samples or entire population, however you call it. Okay, good. So how to use this? This is actually quite helpful. So how to use it? If we do exam and maybe about introduction of biological psychology, for example, there's an exam and then there will be a score, bachelor students, 300 or maybe more. So if we assume that the distribution of the 300 students, they are like normally distributed, I'm curious about what is the 90% of students and what is the score of the 90% quantile students, right? So what I do, I will then basically use the Q-norm function. I enter like 90, 75, then I will be able to get the corresponding score like in the list. So this is pretty helpful. All right, so any questions here? And in R, just one more word, one quick word. So in R, if you want to know it, again, by reading or watching the lecture, if you want to know how the function works, put a question marker in the beginning, and then you will see a lot of the documentation about how to use the function, what the input argument can be, what the outputs can be. There are some examples in the R or R student. Okay. So if you have time at home, what you can do is you can change the location parameter first so that if the mean is around 2.5, so then it will look like this, right? Imagine if you just complete the picture in your mind and fix that in your mind. And if you have another distribution, maybe it is around -5, but wider, it has a larger variance. Imaginably, it will be wider, of course, and also the top will be shorter relative to this. This is because the area under the curve is 1 is always 1. If it is taller, then it's narrower. If it is wider, it's also shorter. So the constant part is the area under the curve, always 1. Good questions. All right, so then if no questions, I assume we go to the next little topic. Discrete function, continuous function, whatever that is, it is only one event. But in reality, we have usually multiple events, or 3, 4, 5, they could happen. And how do we describe the probability of multiple events? And now we are talking about quite a few new terms, maybe 2 new for you. Let me explain one by one. So here they are called joint probability, marginal probability, and conditional probability. So let's take a look. First, the definition, maybe a little bit not so informative, but let's try. So joint probability essentially means the probability of 2 things or multiple things, they happen together or maybe they not happen together. So basically the probability of 2 events altogether. So here the P of raining and also cold outside, it is more or less now. Here just basically means P of raining. So here the P, and I didn't explain this. So P parentheses of rain, this reads as P of rain. So here means reads as P of cold. So here means P of B and A, here is P of A and B, it's P of something, the probability of something. So the P of rain and cold is the probability of rain and the P of cold. So as simple as that. Great. And there's something called marginal probability, and this means the probability of A irrespective of B. Okay. So if I want to know the probability of rain, regardless of code or no code, I will just sum up them together. So I have P of rain together with code, P of rain together with not cold. It can be sunny, it can be 25 degrees, it can still be raining. So here, right? Here, no cold and rain, whatever. Yeah, and then you sum up them together, regardless or irrespective of the other one. You consider only one of them. Right, I don't think this is very helpful. And let me give you an example. So assume that we have two events. One is rain, and we call it X. The other one is cold. We call it Y. And then 1 and 0, the 1 and 0 here, they mean the possible outcome. 1 means yes, rain, 0 means no rain. Here 1 means cold and 0 means no cold, okay? So we have, if you imagine, of course, there are 4 possible outcomes, and then they are like illustrated in this cell, in this table. It can be rain, cold together. It can be no rain, no cold. It can be rain, no cold. It can be no rain, but cold. It's like 4 possible outcomes or combinations. Let's say by calculating the weather from 10 years ago, from now on, just go back to 10 years, and then we summarize the probability of all of the 4 possible outcomes, and then we could give a number of each of the 4 outcomes. So we end up in this kind of table. So here the probability of rain and cold together 0.5, and not rain, not cold together also a little bit higher. Also have a not higher than this, so 0.3. And then the other one is not so rare because this is not a common combination. So here 0.1, 0.1. Okay. So now go back to the 3 possibilities. So each of the number in the cell, they are the joint probability. So if you write it, you could write P of rain equals 1. I can write it. Maybe I have it. Yes, I have it. For the joint probability, so P of rain equals 0, then this column. And then I also go to Y equals 1. Then I go to this value, right? So here, joint probability. Then 0.1, this number. So each of the 4 numbers, they are joint probability. And we also know that if you sum up the 4 numbers, they sum up to 1. It must be the case. It has to be the case. So then move on to marginal probability. And then this is the one I said I interested in one dimension, irrespective of the other. So what that means, let's say I am interested in P of X equal 1. Okay, I'm interested in this. And then I have to work out that there are multiple possibilities in this case, not so many, but only like 2. It can be that when X equals 1 and Y equals 1, it can also be that when X equals 1, but Y equals 0, right? So the other dimension, I have to count them all together and sum it together. Then it becomes the X of 1. So if you look at this on the table, where is it? So X equals 1, Y equals 1 is this number. X equals 1, Y equals 0, then it is this number. And if you sum it together, this is 0.6, right? This is 0.6. And then this is the entire column, because I'm only interested in X equals 1. So then I go to these 2 values and then I write it down here. And interestingly, the place I wrote this number here, it happens to be the margin of the table. So historically, this is called a marginal distribution. This is the only reason, I think. But marginal probability. It has nothing to do really with margins. It has something to do with I'm interested in one dimension irrespective, regardless of all the others. Okay, great. Now a few examples from the table. So if let's say I'm interested in P of y equals 1. So here I go to the table. When y equals 1, x can be 1, x can be 0. I have to sum up these two numbers together, 0.5, 0.1, and then I get another 0.6. Is also a marginal distribution. Marginal probability, if I write it here. Okay, 0.6. Again, it appears to be the margin of the table. One more example to make you really familiar with the calculation. When x equals 0, it can also be that y can be 1, y can be 0, but I don't care about it. I then have to sum up all of them, both of them together, in this case 0.4, right? So I get 0.4. So here, look at this. This is the sum sign. That's why I explained to you earlier. So I sum over all the possible y here, and then the x is the specific x. And then I get the marginal probability, irrespective of y. I'm only looking at x. Okay, that makes sense? And then the last one, I didn't even show you the explanation because I guess this doesn't really make sense without showing the example here. So conditional probability. What is a conditional probability? Well, so conditional probability first, it has a format. So the way to write it is quite specific. We have P, and in parentheses we have X, right? Good. P of X is the marginal probability of X, assuming there are really multiple, not only X. But if we do not care about it, we only care about X, this is the marginal probability of X. We know Pxy. This is the joint probability, good, X. Conditional probability is this. So whenever you see there is a bar, a vertical bar in the parentheses, this means conditional probability, meaning what is the probability of X conditional on Y. Okay, this is the meaning. So how to read it, you might wonder also how to read it. This reads here P of X and Y. The last one is P of X given Y. So this is the condition. Given the condition is there, what is the probability of X, P of X given Y? All right, good. Now you can think about it together with me. So if for example, I am interested in probability of X equals 1, but given Y is also 1. Okay. So tell me, you know the table, you know everything. So tell me what is the results? What is the results of P of X equals 1 given Y also equals 1? Maybe 20 seconds is not enough. Well, should be, but you can think about it for 2 minutes maybe. You have the table, you have everything, so think about it. Given X equals Y, then what is the probability of X equals 1 as well? You have a lot of 0.5, but unfortunately, this is not correct. So think more. Yeah. Now you are getting there. Yes. 5/6 is correct. Yes. Good. So the way to look at it is this. So what is the condition here? The condition, so let me go to one step earlier. Probability describes uncertainty. And if there is a condition, that means the condition part, there's no uncertainty. We know it. So given x equals y, then that means we will only look at this row. There's no uncertainty regarding y. Y can be 1, y can be 2, but if I know that is condition, so then I will only look at here. Y is 1 for sure. This is fixed, okay? Given y is 1, then what is the possibility of x also being 1? So now you nailed down from 4 possible events to 2 possible events, because when y equals 1, there can only be these 2 events. The numerator 0.5, well, this is no surprise. The only interesting part is the denominator, how to calculate it. Well, so it turns out that we can do a plus 0.5 plus 0.1. Yeah, let me do this. So this is the conditional probability of y equals 1, of x equals 1, given y is 1, okay? This is the conditional probability. Does that make sense? Yeah. So the condition is like you reduce the uncertainty and then nail down to these 2 possible events. So now I give you another chance. I think now everyone should be able to solve it. Say, well, I'm interested in, well, when y equals 0, I'm interested in this. Okay, let's write down in the chat. What do you think? Yeah, great, perfect. So similar idea, right? Because now let's say if we have y equals 0 to be the condition, well, we have here this row. Now we have 2 possible outcomes here and here, and now we are interested in when y equals 0. So then this is a numerator, and the denominator is the together 0.3 together with 0.1, 0.4. So the answer is yes, everyone's correct for those who wrote 3/4. Yeah. So now we know the calculation example. Maybe we want to know the rules, like here, right? We want to know the generic form of conditional probability. So here we can go a little bit down to see how that works. Well, here I show you. Yeah, the conditional probability is like this. So the x-axis, well, not x-axis. When let's say we are interested in capital X equals X given capital Y equals Y, and then the numerator is always like the joint probability of it. Yeah. And here, the denominator, what is that? This is actually the marginal probability, because we are only interested in the y part, regardless of x. And then if we want to know how to calculate, well, P of y equals y follows this equation. So the denominator is actually a marginal probability. Does that make sense? Yeah. Think about it, if that makes sense. So now with this calculation examples, we can go back to the definition. It's a little bit get away around, but I think that should work. So conditional probability in a little bit more generic form, P of A given B, it reads as P of A given B. So event B is fixed, no uncertainty. And there is a quite interesting relationship. So the joint probability equals the conditional probability multiplies with the marginal probability. Okay, so the one I showed you, like the previous slide, but the slide next, what I showed you is that if you are interested in this conditional probability, what you do is that you will calculate the joint probability and divide it by the marginal probability, right? So what do you do now here? Well, if you say, I want this, so I multiply this one to be here. So P of B. Yeah, so this is the same equation here. So P of A and B equals P of A given B multiplies P of B. Well, from the math, it makes sense. And we also want to know some intuition. So conceptually, how to make sense of it is actually also quite straightforward. So think about this way. In statistics or in whatever, anything related to statistics, there are usually multiple terms in longer products. So it can be P of something multiplied with P of something, P of something, P of something else, okay? It can be super complicated. We will see something in the later lectures. My approach is always to look at from the right-hand side, from the rightmost term. So now we know P of B. Okay, good. We know P of B easy. And when we know P of B, and then given that I want to know P of A. So this is how that works. You know this first, and then the uncertainty is not reduced, but described by P of B. And then given P of B, you want to know P of A. So this can be expanded actually, and then there can be many, many things. Yeah. It can be that I just quickly make up one, maybe not sure if that's actually the case. I have 3 events. Yeah. B, C, P of C. Yeah, kind of. So at first, I always read it from the right-hand side, the rightmost. P of C, some uncertainty there, and given C, P of B, and then given B, P of A. So then here, this is like the way to describe it. So what is that then? If you think about it, this is the P of ABC, right? Together, the joint probability. Can you abstract? I think that's convinced you, and that makes sense to know everything. But the example I gave you, like the rain and then cold, is a simplified and discrete example. Rain, 2 possible outcomes. Cold, 2 possible outcomes. But in a larger field of research, we are dealing with continuous events, right? So what are the joint, marginal, and conditional probability for continuous events? How does that look like? So now I'm giving you some plots. So suppose we have now 2 random variables, x and y, and they have a joint shape. So the joint probability or the joint probability distribution is described by this cloud. So each dot on it, this corresponds to the probability of y equals something or y equals something, okay? And if you want to use the terminology that applied to discrete event, this is the same. This is the same. So let's say if this is a dot, no, red and green doesn't work well. Blue. Yeah, okay, it's better. So there is a dot. This is capital X, assume this is small x. This is a capital Y, and then this is small y, okay? And then this dot, what is that? This dot is the joint probability of capital X equals small x and comma capital Y equals smaller y. Yeah, same thing. So joint probability, good. What else? We have in the second place, we have a marginal distribution. It also appears at a margin, but it doesn't work for higher dimensions. But anyway, it works like this. So we have 2 events, x one more time and y. Let's say I'm not care about this anymore. I only want to know the distribution of x. So then you take like the margin, you will be able to derive or extract the distribution of X irrespective of Y. Similarly, you can do the same for the Y events, irrespective of X. Okay, good. So the previous terminology or expression still works here. So if I am interested in probability of X, then I do here probability of X, comma Y, but I don't care about it. Then what I should do? I will have to sum up all the possible Y here, all the possible Y here. So that means I will do it regardless. I don't care about it. Now there's a little bit trick here. So Y, we know the variable Y, it is a continuous event, right? How can we sum it up? We will sum it up for ages. This doesn't work. So instead, we will have to do the integral. So we will have to integrate this thing, xy, and then and then this is the variable that you don't care. Well, you want to integrate together. You want to integrate from negative infinity to positive infinity. Yeah, it's just terminology. Don't worry about that. And the plot is more important. So we have a joint space, and here, they are the marginal space. That's very important. Last one, we have the conditional probability, like P of A given B, P of A given B. So what is that? So P of A given B in this kind of continuous space looks like the curve I gave you here, X, Y, and again. So here, let's say Y1, here Y2, and 3, 4, 5, 6 until 6, okay? So here, this distribution means probability of X given Y equals Y1, yeah? And then here, this is the same, P of X given Y equals Y6. So the idea is when you have the joint, now we are here, if you have a joint distribution, you draw a line, then you are interested in the distribution given this line, so conditional probability. It applies as well to the other dimension. So if we draw a line here, and then we can somehow get a distribution. So this is the probability distribution given given X equals small x, here small x, x0, yeah, P of Y. So marginal, conditional probability, same. Good. Or everything makes sense, I guess. Great. So if no more questions, we can actually introduce the Bayes rule. This is the most important part and the most exciting part, but actually super straightforward. We know that suppose we have two events A and B, and we know that we could write P of A and B the same way as P of B and A. The order doesn't matter. These are the same. And according to the rule that we introduced like 5 minutes earlier, we could expand it. So P of A comma B equals P of A given B multiplied P of B. And we could do the same for P of B and A, right? So here this equals to P of B given A times P of A, the same. So because the left-hand side, these two parts, they are the same, they're identical. Here, these two parts, they have to be identical as well. So then you could end up with this kind of expression. Now let's say we are interested in this expression. We put it at the left-hand side of the equation, and we put this P of B to the other end. So hooray, we have a Bayes equation. This is the Bayes equation. Everyone can know it. If you forget, you will be able to derive it, actually. Now let's go to here. So here, Bayes rule here. So P of A given B equals P of B given A times P of A divided by P of B. Bayes rule, we have it. Great. And if you forget, the first way is to write down P of A expanded, P of A comma B expanded, P of B comma A expanded, and then do this a little bit calculation, you get it. So this is one way to like always, you won't remember, you won't forget, you will always remember it. First approach. The second approach is to know the semantic meaning of it a little bit. So the left-hand side is P of something given something, okay, doesn't matter, P of something given something. And the numerator is always first the reverse of it, okay? So the B and the A, they are reversed. And now here, because the P of A is the condition, yeah? And we will know, well, what is the P of A then? So here, remember, always looking from the right to the left. So here, makes better sense. This makes better sense. We have P of A, and then given A, what is P of B? Yeah, good. And then the denominator is here, the left part, the right part, the right-hand side of this. You could also imagine that, well, this can only be P of B, because if this is P of A, this is also P of A, they cancel out, it doesn't make sense anymore. So this can only be P of B. So there are multiple ways you can always remember it. There is no way you forget, I think. Good. Any questions? This is actually quite straightforward. All right. So if not, let's have a few examples. If we have another kind of expanded version of the rain and the cold example, the rain and the cold is simple, like only two events of rain. So rain, no rain, cold, rain, cold, no cold, right? Suppose that we have a slightly complex example. So we have eye colors and the hair colors. So people have different eye colors from brown to green, and also hair colors from black to blonde, something like that. There can be more. So let's reduce it to be 4 colors. So in total, we will have a 4x4 matrix. So 16 possible events, 16 possible outcomes. So all of the numbers here, each of the numbers, they are joint probabilities. Yeah, right? And also we could sum up this per row. And here, for instance, is 0.36 and 0.37. They are the marginal probabilities. So now say I'm only interested in the eye color of blue, regardless of the hair color. Well, then of course, I sum all of the possible instances here when it is blue and sum it up, then that becomes the marginal probability. I can do the same for the hair color. So if I'm only interested in brown color, then I will calculate regardless of the eye color, all of the numbers summing up here equals 0.21. Okay. Similar idea, really the same, even though that is a little bit complex from 2 to 2 to 4 to 4. But however, no matter how large the table is, we could always work out the marginal probabilities. And we could also be able to calculate conditional probabilities. Yeah. Okay, for the last 10 minutes or so, if you don't have questions at this point, I will give you one exercise. A little bit challenging, a little bit tricky, but I think if you understand the meaning of joint, conditional, and marginal probabilities, you will really be able to solve this exercise. This is also quite relevant nowadays for like COVID. So let's say, suppose in the general population, the probability of having the rare disease is 1/1000. So this is a fact. I give you the rare disease, how rare? Well, 1/1000. And we denote the true presence or absence of the disease as the value of a parameter called theta, okay? Theta is a discrete variable here. So it's either presents or no presents. So in this case, it's either a smile face or a sad face. So if it is a sad face here, then that means, well, the person is having the disease. If the happy face, then that means the person is, well, healthy. So negative after the test. And so here, this one, the base rate This one is summarized as P of theta equals set phase equals 1/1000. Okay, so this is terminology. Let's say there's a test, COVID test. It is good, but it is not perfect. So I have a test. So the test for the disease, it has a quite high hit rate. So you might wonder, what is a hit rate? Hit rate 99%. Hit means when the disease is really there, how much accuracy or precision that I'm able to detect it. That's hit. So if there is a disease, I didn't detect it, that's a miss, right? So if you know signal detection theory, then that's other terms. I don't want to go into that part, but hit rate means when the disease is there, then I'm success. So in the statistical terminology, given the disease is present, and I'm giving you the positive test result. Okay, for 99, pretty good, pretty decent. And another assumption is, well, the test is sometimes giving you a false alarm. False alarm, what that means? False alarm means I'm healthy, but the test is telling me, hey, you are positive, right? This is the false alarm. So in the statistical language, given I'm healthy, but the test says I'm positive, yeah, not good, but whatever, 0.5 false alarm rate, 0.5. Now the question, so suppose there's a person, you come to the test center, and then the test result says you're positive. And what is actually the probability that you have the disease? So this is quite interesting question. I don't know if you have disease or not, because I haven't yet tested you. But there is a truth. You either have the disease or not. I don't know. I want to use test to detect it. Now you go to the test center, and then the center says, hey, unfortunately, you are positive. But what is actually you are sick or not? This is the question. Great. And translating that to a statistical question or terminology. So given the test is positive, how likely you are really sick? Yeah. Oops. So do it. Use your pen, paper, and give me a number. We can have the rest of this lecture, 5 minutes or so, to work on that. I encourage you to work on it. So what do you do? A little tip. So here is a conditional probability, right? First of all, expand it using the Bayes rule and find out what number can be plugged in, what number is unknown, but can be derived from here, the conditions I'm giving you, this slide. Okay, do it. Okay, any ideas? So there are three. Is there three? So sorry. There are three answers from the chat. One is 66%, the other one is 2%, and then the other one is even 0.1%. Any more ideas? The answer. So the answer is, I'm showing you here, and then I'll explain. So the answer is here, like 2%. So the correct way to calculate it is just as I said. First of all, this is our target. Well, maybe red. This is our target. First of all, expand it using the Bayes rule, right? So using the Bayes rule, we can have the equation on the right-hand side. Well, we know this. This is the Bayes rate. And we also know this. This is a hit rate. We don't know yet the denominator, but that is actually the marginal probability. Yeah, the marginal probability of here, of this positive. So marginal probability of being positive, it can be that there is there is the heat. It can also be that when the disease is not there, but then it's still positive, and that's the first alarm. So then we use here as the denominator. Then we get like the final results. Make sense? So essentially, what you can learn from here is that no matter all of this kind of test says I can get a 99%, 99.99% of like hit rate, you still don't know the first alarm. And also the most important thing is the Bayes rate. The Bayes rate is 1/1000. You get a person come in and you get a positive results. What do we know? Well, still the probability is small, is very small. Well, for COVID it's different because it's contagious. So it's not a rare thing, but for like a regular rare disease, the Bayes rate, this is very important. Okay, good. Questions? Yeah, we're right on time. Any questions? So if for any of you who didn't get this answer, not 2%, I really encourage you to finish up the calculation immediately afterwards. You can have your time, and or maybe you don't have the slides. Yeah, if once you get the slides, you can do the calculation and then to finish it. Yeah, and then you have a really better understanding of how this Bayes rule works. And then from next week, we'll talk about something else. Good. So if everything's okay, then I guess we're good. And let me know if you have. Oh, wait.